Thank you. And it's really a pleasure to come here again and finally meet so many people in person. So every time I come here, I feel a little nervous because this summer school is called Neuro, but I feel my work is not so neuro. But until Louis told me that the C can mean many things. For example, it can be China, it can be cognition, can be everything. So look at the logo of my lab. It looks like a brain, but if you look at it carefully, it's written in the Bayes theorem. So it's just a mathematical equations looking like a brain. Many of my work is about probability, or if I say, no matter where I go, I find it finally goes to probability because I share the belief of Laplace that the most important questions of life, which are indeed, for the most part, only problems in probability. If you don't believe it, let's start with an example. How many people here heard about the Monty Hall problem? Good. About 1/3 to one half. For those of you who did not hear it before, let's start with the description. So Monty Hall is a TV host, and his in his show, there are 3 doors labeled 1, 2, 3 on the stage. And behind one of them is a car, and behind the other 2 are goats. So as a guest, you will guess which door hides the car. If you correctly choose it, you get a car, otherwise nothing. Even no goats. Okay, so let's make it simpler. Suppose among these 3 doors, you initially choose one, and then the host comes. He does one thing. So the 2 and 3 are rows you did not choose. And the host would open a door to reveal a goat, like this, the 3. And then the host asks you a question. Will you choose to switch to the remaining door, the 2, or would you like to stay at 1? What's your choice? And why? Yes. Okay. So you learned from, yes. Yeah. For those who never heard about this problem, did you have any idea that, like, it's the same whether you switch or not? Any kind of beliefs? So why? What's your reasoning? Good. So we have both correct answers and errors, and we'll see what's the models in your mind. For this problem, there are several solutions, and it may remind you several approaches to understanding human cognition or what humans really do. So one way to do it is learning from the real or simulated experiences. For example, you can watch, you can take statistics of what have been the previous host, previous guest, what they have chose, whether how likely it is to win by switch or win by stay. Or you can just do simulations. It can give you 2/3 and 1/3. So this is the answer, but you don't know what's happening behind. This is one solution. Solution 2 is you can change the representation of the problem. And this is also someone who has said, oh, if you choose a stay, then it means you are choosing one door. But if you choosing to switch, if you don't consider what's happening after the host opens the door, but right at the right beginning means you actually have 2 doors. So still it's 1/3 and 2/3. But what I'm going to tell you now is this problem can be solved by Bayesian inference. Actually, every problem about probability can be solved by Bayesian inference. So here's how. So I'm going to make you familiar with this procedure. First, we need a generative model. The generative model, let's say we use R to denote where the car is hidden. So R can be car or reward, no matter. So in this case, if you see nothing, you just guess, then the probability or your prior belief for where the car is 1/3 for each door. And then suppose you choose the door 1. So the choice C equals 1. Then what the host does, where the host opens, actually depends both on where the car is and which door you chose. So here, host opens door 3. As you can see, if the car is behind door 1, then the host just randomly opens 2 or 3. But if the car is behind the door 3, there's no chance the host will open it. He will open the door 2. So this is where the information comes. So what you can do is, based on the new observation, what the host does, you do a Bayesian inference. So here's the prior, likelihood, and posterior. Yes? Yeah. That's a key. So the host always reveals a goat, never reveals a car. Yeah. So you have prior belief about where the car is, and the likelihood depending on which door the host opens. You have likelihood. And what you need to do is just to multiply the prior with the likelihood. And so here's what follows the Bayes theorem or Bayes rule. It's just we can use the posterior likelihood ratio, which we just drops the denominator because that's difficult to compute. We can just use a ratio, and it's simply the prior ratio, the times the likelihood ratio, the prior odds times the likelihood ratio. So it's simple. It's 1/2. So you have 1/3 and 2/3 respectively for the door 1, the stay, or door 2 switch. That's the end. So this is a Bayesian inference solution to the problem. But what are Bayesian observer models? I like to use the word Bayesian observer models instead of just Bayesian models because the term Bayesian models can mean two different things. One thing is to use Bayesian method to fit any model and to compare using a Bayesian measures of like model comparison measures. So for the Bayesian modeling, for any of you who have already done so, you're probably familiar with like STAN, like PyMC, like I also suggest this book by Michael Lee and Wackermakers. But by Bayesian observer models, we mean different things. It means we treat human or human mind, human cognition as kind of work in a Bayesian way. So for this, there is a wonderful textbook by Wei Ma and Conrad Coding and Daniel Goldenrich. So if you want to know more about it, please read the book. I have just showed you like a Bayesian observer for this multi-hole problem. The observer has a generated model and then solve it with Bayesian inference. But you may be wondering, so Bayesian inference is kind of normative, means it tells you what you should do when you face a specific problem. But people are not necessarily correct, right? At least some of you think it's the same whether to switch or to stay. So how may the Bayesian modeling approach, how may a Bayesian observer can describe incorrect responses? Do you have any idea? Possibly. Yes? I think both of you are close. So what I like to say is you can still do Bayesian inference, but your generated model can be incorrect. Because generated model is not necessarily what happens in the real world. It's just beliefs. It's just your subjective beliefs. So it can be inconsistent with the ground truth. So here, if you believe that the host choice is independent of where the car is, then you just miss the link from the R to the H, then you will think, oh, no matter the host chooses, it had nothing to do with the reward probability of each door. And then you will reach the incorrect answer of like it's the same for the two doors, whether I switch or not. Yes, that's one way. What I like to talk is also about like Bayesian observers not only follow Bayesian inference, but also maximize expected gain. So let's have a more complete example of the like Bayesian decision theory. Bayesian decision theory is simply a normative theory on how to act under uncertainty. So we start with a stimulus, say it's X, and based on X, you can compute the likelihood of what kind of world are you in. And you can also like combine it with your prior belief about the world. So by Bayesian inference, you get a posterior. And this is a part we have already done, the Bayesian inference. At the same time, we have a gain function from this world or some world. And to make decisions, you have to combine this gain with the posterior beliefs, posterior probability. If you put in equations, it's the Bayesian decision theory means you should choose the decision rule called D. It maximizes the base gain. So simply look like this. Another way to understand it is just you have a gain function and you try to marginalize over possible stimuli and world. Let's look at an example, probably the simplest one. It's called signal detection. You probably have heard like signal detection theory. So basically, is you have a stimulus, and it can either be a signal or noise. What you need to do is make a binary choice, signal or noise. Let's call it S or S bar. It can be many different things. For example, when a doctor looks at this image, it will judge, whether this one is a tumor or not. Or is this mushroom poisonous or edible? Or is this suspect guilty or innocent? Just binary choice. And let we start with the generative model and likelihood. In this problem, it's just very simple. You have a latent world you don't know, you can't observe directly, and you have from it generate a stimulus you can directly observe. What you need to do is to judge which world are you in, the signal or noise based on the stimulus you observe. The two Gaussian plots are probably you guys most familiar with when thinking about signal detection theory. So each Gaussian denotes, like left one, it denotes if it's a noise, then what's the distribution of the possible stimulus value. And the S on the right is for the signal. And based on these distributions, you have the likelihood function. So here, the likelihood function is just the probability density function. Just look at it in a different way. For example, if you observe an X at this point, then your likelihood that this stimulus comes from a signal is here, and from a noise is here. However, it's not necessary to be Gaussian. The likelihood function can be everything. So for more complex or more real-life stimuli, it can have very arbitrary. For example, you may have if it's a poisonous mushroom, it may look like this. Or if it's an edible mushroom, look like this. So it's not necessarily Gaussian. But signal detection theory can still work here. It's the same. Just look at the likelihood function. Yes. W means the world, the possible state of the world. So in this problem, it's signal or noise. So signal or noise are the two possible states of the world. So W is a random variable, and its value could be signal, could be noise. So again, here we have likelihood. So this is a part of likelihood. And the full decision problem also depends on, say, the gain function. So we can, for this problem, because we have two possible states of the world, signal versus noise, S versus S bar, the capital one. And we can write the possible action of the small letter s or small letter s bar as a possible action, you choose, oh, this is a signal, or you judge it to be a noise. So now we have the gain function could be described by a 2x2 table. You probably heard about this. So if it's a signal and you say it's a signal, so this is pitch. And if signal, you say noise, you miss. If it's not a signal and you think it's a signal, then it's false alarm. And if it's not signal, it's a noise, and you say it's a noise, it's correct rejection. So it's 2x2 table. And if we have the 2x2 table, the gain function look like this way. It means whenever you are correct, it's the same. Whenever you are incorrect, it's also the same, no matter it's a signal or noise. So in this case, maximizing gain just equals maximizing accuracy. It's just like our Monty Hall problem. You don't trade off anything. You just choose the option with the highest probability to be correct. But the world does not always look like this. You may see gain function like this. So in this table, what I changed is at the right upper corner. So now, even you are false alarm, you don't lose anything. You get 1 point. Now tell me, what would be your choice if you are facing this kind of gain function? Always signal. Yeah, because now the action, like choosing signal, it says dominates the noise, because no matter whether a word is signal or noise, it's always not worth to choose signal, to say this is signal. It can also look like this. So what I changed is the left lower corner. So you see what? I decreased the value, the gain for if it's signal, but you miss. It now becomes a penalty. It's worse than if it's a noise and you say it's a signal. It's also, that is, miss is more costly than false alarm. It's also a very common case. For example, if the patient gets tumor, but you miss it as a doctor, you miss it, then it's bad. It's worse than if it's not a tumor, but you tell the patient it's a tumor. Okay, so in general, we can denote it with a gain function. Use the smaller case as action and the capital as state. Yes. Uh, when we treat it as a normative problem, we just assume that this is what you get from the outer environment. But of course, because if this is something like the observer, computation happens in the observer's mind, then it's possible that you misperceive the gain function. Yeah, but just say if the gain function is like this, what's your optimal choice? Yes. Yeah. The third. No, no, you don't need to have them like sum to one or anything. The gain could be any value, any real number. You don't have the constraint of they have to one. Yeah, because probably it's a little confusing because you often see the 2x2 table, but it's the probability of hit, probability of false alarm. In that case, you need to sum up to 1. But here, we use a table to take down the gain function, the gain you will receive if you are in this situation. Yeah. Yeah. I mean, I think you are referring to this case. Mhm. You mean in this case? Oh, it's different because you look at each column. Like each column, the upper one is larger than the lower one, right? Yeah, but in this case, it's not the same. Like 1 is larger than -1, but 0 is smaller than 1. Yeah, so this one is not dominant. Okay, the last piece, the prior. So with the prior, we need to have the probability to be a signal and probability to be a noise. They add up to 1. So the prior belief, the 2. And with this or everything in piece, we can just put them together. And with some very simple derivations, you will reach this equation. So it's simply you compute kind of this is the prior odds, this is likelihood ratio, and here is the gain function in some way. They have some kind of ratio. You just multiply them together, and you get a statistic called z, and then you just follow this simple rule. If z is greater than 1, then you choose signal. Otherwise, you choose the noise. What's interesting about this equation is, as you can see, in some way, the prior belief and likelihood ratio and even again, it's kind of exchangeable, right? If you want to reach you can create, you can change, for example, you can change the gain functions to switch the threshold. You can also switch by change the prior beliefs. So this is kind of feature of the Bayesian inference. Like in which ways you can manipulate the problem to change the optimal solution for this. Okay. Up to now, this is just the kind of statistical thing. But what you and I are more interested is a human Bayesian, or even an animal's Bayesian. I was much inspired by this book. It's just like its title. It's straightforward. Perception as Bayesian inference. It's kind of old book, like back to almost 30 years. And in the book, actually, it's a collection of papers. And they try to explain many perceptual phenomena, like visual illusions, as kind of from the perspective of Bayesian inference. Like, say, because the environment statistics look like this, and people are trying to make the Bayesian inference, so that's why they have such kind of illusions or biases. I'm going to give you a quick overview of the different types of Bayesian observer models applied in different areas, and then give you 2 in-depth examples. So basically, many applications of Bayesian observer model is about information integration. A classical example is by Ernst and Banks. They show how people may integrate information from the visual modality and the haptic modality. It's like in their experiment, they created a virtual, here is a virtual box, and the participants, they judge what's the height of this virtual box based on their visual information and haptic information. Because this is kind of virtual environment, so experimenters can manipulate these two modalities separately. And what the model did, the assumption is, although the two modalities may not agree with each other, people may believe that their visual stimulus and their haptic stimulus, they come from the same stimulus. So they can think of like, you can think like both of them come from same stimulus, but because percepts has noise, so it can look different. And it's very simple to develop the optimal solutions for this problem. It's like if you assume each come from a Gaussian distribution with its different variance, then the optimal solution will be you have a linear average, you have a weighted average of these two percepts with a weight assigned to each modality proportional to its precision. So precision is the inverse of the variance. And this study inspires many following studies. For example, the information to be integrated not necessarily come from different modalities. It can come from different people. If two of us, we watch the same stimulus, the same like noisy one, then we both have our noise copy percept, then we can communicate with each other and come with a final decision, what's this? And it can also be integration with your percept with a prior belief. For example, in Galerieri and Sutherland's work, they ask people just to reproduce a temporal interval. But the temporal interval could be in a block of short intervals, or middle intervals, or a long intervals, 3 different blocks. What they found is, apparently, participants' reproduction, they biases towards the center of the block, the interval block. And it also shows something like if the bias is largest with the longest interval. And this is not an exception, but kind of rule in the perception areas. And there are many similar phenomena. It looks like regression towards mean. And it can be kind of explained by Bayesian observer models. And I'm also happy that in this morning, Sukbin has already talked about the efficient coding, so I'm not going to more details here. So for Bayesian inference, you can only explain that it's like the bias is towards the mean. But with the efficient coding, it's a force in the opposite direction. So with the two together, you can explain more biases in human behaviors like this. And this kind of modeling is not limited to perception. We can also do it with more abstract magnitudes, for example, for value or probability in decision making. And in previous cases, it's like you know that the stimulus, different stimulus, they come from the same source. But in many other cases, we don't know, like whether it's one source or several sources. So this is a typical problem of inferring the latent structures of your observations. There's one work that inspired me, like clustering in working memory. So, okay, this morning's talk is also like have Supkin also talk about kind of clustering. So, but we look at it from a different perspective. Like here, if you look at location of the six stimuli, they seem to follow like 4 into 3 clusters. And Oh and Jacob work, they are trying to say like no matter these stimuli look like, people have a tendency to cluster the items into clusters. Like they are trying to build a hierarchical model. Say, oh, these stimuli, they may come from several different clusters, and each cluster may have one or several stimuli. Like their working memory is subject to this kind of inference, and why it may have biases towards some centers or have some kind of. And similar problems, it happens in areas called categorization or how people learn concepts. And we will talk about that in more detail soon. And we also did some work in learning distributions. And this is what I'm going to talk in my next lecture. Why learning distribution could be a difficult problem or a computational challenge. Think about you have samples. And you are trying to infer what's the latent structure behind it. What's the distribution that has generated these samples? As we know, the possibilities are in fact infinite. If you don't have specific constraint on the distribution, for example, if the distribution is not necessarily Gaussian, then the space for your distributions are infinite, and it looks like you have to choose one in infinite large space. So that's a challenge. That's also what I'm going to talk about like in our next lecture. And such learning latent structures is also a very common case. Like if you have a dynamic environment, say you have two, like the multi-armed bandit, you have two arms, but their values may change from time to time across time, like change across time. That's a typical task that Nathaniel used before. And in such cases, you need to infer so whether a change has happened or not. And according to George Tannenbaum, like such kind of like Bayesian inference may underlie all kind of learning, like how we build a structured or hierarchical knowledge system. So I'm going to walk you through some examples to get some flavor of this. This definitely not a full list, but just some flavor. So one example is about hierarchical Bayesian observer, and also we'll see. Okay, so in this task, it's very simple. Participants will hear a sound and at the same time see some visual stimulus, a light. And what the participant need to do is to report where the sound is. That's a localization task. So in this task, the participant does not necessarily rely on any visual information. He can just report on his auditory, based on his auditory modality. But the problem here is if there is a auditory information and here is the visual information, because author information is not so accurate about, it's more noisy about the location. So people are likely to use their visual information to help them to localize. And the authors develop several different models or Bayesian. And here is the causal structure or the generated model they assume. This problem is more complex than the previous, like visual and haptic one. It's like it considers two different cases. The participant may think, oh, these two modalities, they come from the same stimulus. This is the same as before, but they may have a different belief, like, oh, this visual stimulus and this auditory stimulus, they are totally different. So they have nothing to do with each other. And by this hierarchical model, participants will base on their observations to infer whether they have the same source or they have two different sources. So this is a hierarchical model. Is it clear? Okay. Oh, yes? Yeah. It's like as experimenters, we generate our stimuli based on some model or some procedures. But when we model participants' behavior, we assume they have some internal model. Yeah, that's also my next slide. Like I show you, there is an observer's model and there is experimenter's model. And based on the Bayesian inference, there are several things the observer could do. Like the authors assume they may like combine these two information. It's like if you think, oh, there is a 0.7 probability, it's one source, and it's 0.3 probability, it's two sources, then the participant will combine the predictions from these two possibilities according to their likelihood of probability. So this is called model averaging. It's also similar to if you are running models to fit your data, and you find a model 1 has 0.7 probability, model 2 has 0.3 probability to exceed, then you are just averaging them. And it's also very, it's a very common technique in machine learning literature. And they may also just do model selection. That means choose the best model that fits the data. Here model, I mean the internal model of the observer. And there can also be property matching, means participants just use one model, but they use the model, they have a stochastic choice, like 0.7 probability to use the one source model and 0.3 probability to use the two source model. And each of these different, we say, the way to generate their combine to go from their inference to a final choice, they follow some, like they satisfy some loss function to maximize or minimize loss with such kind of loss. Like model averaging is to minimize the squared error loss. And the model selection is to maximize the probability of choosing the correct causal structures. Like if your loss is 1-0 loss, then it's the best choice. But probability matching is always suboptimal. But so how did the authors know like which of these cognitive models best describes participants' behaviors? So what they did is to vary the distance between the location of the visual one and the location of the auditory one. And the three models will give different predictions, different prediction patterns for these different conditions. And this is also they fit their model to the data, the behavioral data, and found that actually the matching matching model best describes the most subjects' behaviors. Okay. Yes. Oh, it's the percentage of participants. Yeah, so for each participant, they run the three models and see which model fits the data best. Yeah. And here is another example. It's a very old work in 1990s. I think many of you were not born at that time. But it's very inspiring. Like I found John Anderson has many works that's so inspiring even up to now. Like so what he proposed at that time is he actually wrote a book. It's called The Adaptive Character of Sort. And the categorization is just one case. So what he tried to do is model human categorization as an optimal solution to the environmental constraints. So in our previous case, we had like participants were trying to infer the latent structure of the world. However, the latent structure is kind of finite. It's just either one source or two sources. But in real life, humans may invent new categories as needed. That means we may have infinitely many different cases, different categories. For example, this is just a screenshot of my note app. Like this is, the tag, and you can create the tag at any time. So the computational challenge is, how can Bayesian observers introduce new categories on the fly? One solution to this is a random process called Chinese restaurant process. If I describe it in one sentence, it's just the rich get richer. For those who never saw this before, let me show you something. So first I need to clarify that this is not the Chinese restaurant I'm familiar with in China. It's more a Chinese restaurant in the Chinatown of like in New York City, because it's so crowded and the restaurant is so small. So suppose you enter in a restaurant, there are many tables, round tables. And now each table sees some customers. And here comes a new customer. And which table will the customer join? So the assumption is, it's probably quite counterintuitive to our common sense. Like, if it's me, then I'd like to go to a new table. Definitely. I don't like to share my table with strangers. But here, it assumes that the probability you join the table is proportional to the number of customers at the table. So if it's a new table, then it has a parameter alpha. You have probability to join it. So let's see just an example. So here we have like, suppose alpha equals 1, then you just count 4, 3, 1, 0. Then the probability the new customer joins the first table would be 4/9, and the second one is 3/9, 1/3, something like this. Yes. Sorry? What's that? Oh, okay. The alpha is a probability you will, it's like a pseudo count for the new table. It's like the probability you join each table is proportional to the count of customers at each table. But for the new table, you give it alpha, always alpha. So it's here. It's the probability you join a new table will be alpha 1 over like n plus alpha. So it's 8 customers. It's 1 plus 8 is 9. It's 1 over 9. So here is also 1 over 9 because this is one customer. This is a pseudo count one customer for the new tables. So as you see, like it is kind of rich gets richer, but you can still create new tables, new categories. What? No. No, so here we assume this is a restaurant with infinitely many tables, and each table can seat infinitely many customers. Yeah, it's an analog. Just yeah, I think it's easier to memorize this kind of thing in your mind, despite it makes no sense in the real world. Okay, what's interesting about this translation process, the CRP, is if you use as a prior, it's a distribution over distributions. So let me show you what it looks like. So assume alpha is equals 1, and if there is one customer, definitely it takes just his own table or her own table. And then it comes a second customer, and then it comes two possibilities. This new customer either joins a new table or creates their new or joins the old table. And as we can calculate based on the alpha over alpha plus n, you can see it's 1/2 and 1/2. And here comes a new customer again. And if you go from here, then you have 2/3 and 1/3 like this. Or you go from the second probability, then you like diverge into these three probabilities. So when there are 3 customers in restaurant, then you have 1, 2, 3, 4, 5 different distributions over the tables. And what the CRP prior is about was the distribution over this distribution. As you can see, it's 2/3, 1/3. Sorry, you need to multiply this with this. So this would be like 1/3, 1/6, 1/6, 1/6, 1/6. This needs to add up to 1. Is it clear? Okay, go ahead. So what's this to do with the categorization as Bayesian inference? We need a more complete generative process. So before, we just specify that you have some categories and you can go to some categories, but it has nothing to do with what the stimulus look like. And in previous table, we just plot each customer as a circle, and each circle looks the same. But actually, each stimulus is different. So we may use such kind of bar, like a white, gray, black, like is this a 5-digit? Like to use it to denote a stimulus. What you assume is, if we need to create a new customer or here a new stimulus, then what we do is first we choose whether which cluster or which table it may join. So for example, if this stimulus joins an existing table, then it will be created based on the phenotype, the phenotype of this table. So each table has a phenotype. So now it becomes a new stimulus. If instead you are going to create a new stimulus from new table, then first you need to do is generate a new phenotype. Sorry. No, I'm just, because I often confuse like stereotype with, so I'm not sure whether it's the correct word, but you understand it. Okay. Okay. And then you have this one, like, and then you generate stimulus from this table. So in this way, you can generate stimulus by stimulus just from scratch, from nothing. So this is a full generate process, we assume. And yes. And in this case, we can assume a very simple rule, like it has 5 digits. So each digit, it may be generated from this one. I think it's this is yeah. And what you can see is each stimulus, actually each digit is either black or white, so it's binary. But this phenotype, it's kind of sorry, I think the word is prototype. Okay, it's a prototype. It makes more sense. It's prototype. So the prototype is kind of like this is a continuous value. So this would be Bernoulli random variable from this, this probability. Yeah. Okay. So after we have the generative process, the remaining thing is just easy. You do the Bayesian inference. Yeah. Let's see. We start from 2. Or maybe we still have some time to work through this. But I'm not sure whether I can get through it clearly. Maybe 15 minutes is better, then I can have more questions. Yeah. Okay. So what Anderson did in 1991, what he had is a CRP-based algorithm. It's not exactly the Bayesian inference, but a kind of approximate one. So let me show you how it goes. So as we did before, he assumed like alpha equals 1, and the value of each category on each dimension is randomly drawn from a uniform distribution. So it would like this. So like you observe a stimulus, the first stimulus, it looks like 1, 1, 1, 1, 1, and so it goes into the first table. And the prototype of the first table would start with 1 half, 1 half, 1 half, 1 half. And then comes the second stimulus. The observer's task would to decide whether this goes into the same table, same category as the first stimulus, or creates a new category. So here's the computation happening in the observer's mind. Like they will compute what's the likelihood of observing this and what's the likelihood of observing that. So it's simply just some probabilistic computation. following like this. So you may come with that. This is finally goes to this. And for the other side is a little bit smaller. So this is 165 and this 156. Yes. Oh, so in their experiment, like the stimulus is what the observer observes. Yeah, like this is the what they observe. So stimulus it comes from outside. Yeah. What did you mean by the sequence? And each the actual stimulus may look like, I think they use some visual stimulus, or I'm not sure. Yeah, but it's basically they have 5 digits and 5 like something like this. Yeah. Yeah. Sorry. Sorry. I should do this. So the subject, the 1, 2 means it's the prototype of the first table or first category, and the prototype of second category. And the superscript means this time 0, 1, time 0, this time 1, or should I say this is the time that before any stimulus is observed in this category. And 1 means, and now we have the first, have 1 stimulus. So from this to this, it integrates this information into this to update the prototype. Yeah, it's like, so here is the category, and if you like assign a new stimulus into this category, then the prototype of this category will be updated. Yeah. Which one? This one? Oh, this is this one. C20. Oh, oh, I see. Because in this case, you don't use the second table, second category, so I simply drop it. Yeah, because this one is just one table, so it has nothing to do with only this one. You come with the second category, so you will need this. Yeah. Yeah. It's not needed in this equation. Yeah. Yes, for the new brand new table, brand new category. Yeah. Or you can say it starts with a uniform distribution. The prototype starts with like this one, like look like this. So it's their start. But after a stimulus is assigned to it, its value will be updated based on the Bayesian inference. Yeah. And every time a new stimulus is assigned to it, the category, the prototype will be updated. Yeah. And approximation, the Anderson did is to choose. So say like a left one, it has a higher posterior likelihood than the right one. Then the observer will just choose this branch. Just leave this out. Just trim it. So the next time the observer will start with this, and then comes new stimulus, and the computation continues. Yes. Yeah. The so this is it's like this is a prior for the prototype. Yeah, that means when you create a new category, it starts with this. Yeah, yeah, yeah. And then it will be updated based on which stimulus come to it. Mm-hmm. Sorry? For the stimulus, this is observation. These are observations. These are known. So what the observer needs to infer is the category, like the category label, like which stimulus belong to the same category. It's like if a new table is the same, all new tables are the same, but each table, its property or its prototype depends on which customers come to the table or which stimuli are assigned to the category. Yes. Yes and no. So let me show you this. So this is a problem. I'll ask you what's the algorithm, not strictly Bayesian pattern approximation. So if it's strictly Bayesian, then it's optimal. It's optimal. It's like Bayesian inference is optimal. You assume, of course, it depends on what kind of internal generated models assume. It's just if you assume the stimuli are generated in this way, then the inference is optimal. It's the best thing you could do. Sorry? Define what stimulus should be. Oh, I mean this. Uh, I mean this generated process. Sorry, could you? Yeah, yeah. Then your inference would be different. So if you assume, for example, you assume each new table will have like the prototype is not 1/2, but like say 1/9 or 1/10, then it can introduce some biases different from this one. Um, I'm not sure exactly what the prediction will be. I know it will be different. Yeah. Exactly. I think it depends on what the stimuli really look like. So if it's, say, you assume that it comes from 1/9, but your stimuli are more like 8/9, something like that, then you are very unlikely to assign them into the new categories because your old categories will become more and more similar to your actual stimuli, but your new category is still very different from that. And so that probably will create like less number of categories than in this way. Uh, for the CRP, it actually can go to infinity. Yeah. So the property of the CRP process is that when the number of samples grows, then the number of categories also goes up. Yeah. Yes. Exactly. Sorry. Actually, let me show this. When we compute the likelihood, how likely this new stimulus belongs to this category, we consider the likelihood is based on like the similarity. Yeah, it's like how similar this one is to the prototype. Yeah. Okay, I'm very happy your questions have clarified this. Okay, so my question is, um, this approximate algorithm. So anyone can tell me that why is this algorithm not strictly Bayesian but an approximation? Yes. No, we have prior. We have everything. We have prior. Like prior here, it says, yeah, this one, the red word. The, the value is drawn from a beta distribution, a uniform. Yes. Exactly. Yeah. That's the that's a step we break from the exact Bayesian. So to know exact Bayesian inferences, you consider different probabilities, but you never drop anyone. It has some probability. So if you have later evidence favoring it, it can come back. But in Anderson's algorithm, it just drop this one. You will never come back to this, even you find later from the samples that this one is more likely. Okay, so I'm just going to show you how to build a Bayesian model step by step, but it's kind of a conceptual one because I'm not giving you any concrete examples. Just you can also refer to this book. I think they have a very good just guide, like step by step guide to this. And basically, the concept I'm going to emphasize is like first you need a generated model. Like in this example, you need to specify what kind of, how you generate stimulus. Like you have some latent variables, how they connect to a stimulus. You actually, the observer, let's say observer and experimenter. Observer actually observes. And then the observer can do the Bayesian inference. And then, based on the inference, the observer will combine their inference with the gain function and possibly also with some noise distribution on their responses to finally come to a response that could be observed by the experimenter. Yeah. So this is the two levels of inferences. Like the internal cycle, internal is the observer's inference. Like the observer will base a stimulus they observe and their prior belief and the gain function, they will do something, their output a response. And then the experimenter needs to base the observer's response to infer the unobservable latent variable as well as some kind of individual, some parameters that may vary from individual to individual. Does not go And just one note. So you know, for the observer, it's Bayesian inference, but you can still fit the Bayesian inference, the Bayesian Bayesian observer model with something not Bayesian, say maximum likelihood estimate. These are two different things. So you can fit a Bayesian observer model with MLE. You can also fit with a Bayesian. If it's two Bayesian, sometimes it's called doubly Bayesian. But not every time we tend to do that because as we know that Bayesian modeling sometimes it needs a higher computational load than the MLE, and if the Bayesian observer model itself is very complex, it's very computational intensive, then you may prefer to do it with the MLE instead of Bayesian for the outside one. Okay. And there are also some rules to follow to construct alternative models. For example, you may vary the generated model. Like to say, you have a different prior belief about the prototype of each category. Or you can vary the decision model, like the first example we showed, like they may do the model averaging, they may do the model selection. And you may also vary the algorithm to approximate the Bayesian inference. For example, you can use specific sampling algorithms that introduce some noises or biases. And you may also construct non-Bayesian observer models, such as heuristic models. And every algorithm model can be counted as a heuristic model. Okay, so far we have learned something about the Bayesian observer model, but what can and can't Bayesian observer model, such kind of modeling approach, tell us? You must have seen these three levels again and again in this summer school. And as we can see, to the lower level is subject to biological constraint. And to the upper level is subject to environmental constraint. And the Bayesian observer model is kind of computational model. So what it solves is kind of the computational problems imposed by the environment. But you can still go more to the biological side or to the more complex things. So there are two directions to go. So if you are interested more in the biological side, you are more interested in developing biologically plausible algorithms, there are many ways to do that. So first thing is, in many cases, the exactly Bayesian inference, Bayesian observer model is just computationally implausible, intractable. So you may want to do, say, like variational Bayes to loosen, to have some approximate algorithm to it. And you may also use reinforcement learning algorithms. And you know, in specific cases, reinforcement learning algorithms can be viewed as an approximation to the Bayesian solution. And similarly, in some other cases, is every evidence accumulation models like drip diffusion models approximate the Bayesian solution. And another commonly used and very useful way to model individual differences is you can modify the solution for Bayesian observer models. For example, here is a work by Jadri et al. They are trying to modeling how individuals, like healthy participants and as well as patients, like how they combine prior and sensory information, like prior and likelihood. So as we know, the correct or the Bayesian thing to do is just to you combine is to multiply the prior with the likelihood. So which means the WP, the prior, is 1, and the WS is 1. But you may modify it a little bit. Suppose you say, okay, I can treat this kind of weight as kind of parameter, and I can make it not to be 1. So this is a kind of weighted Bayesian. It's not really Bayesian. And they also introduced something called circular inference. That is, some information, like prior information, it may be used more than one time, be used multiple times, or the sensory information may be used multiple times. So all of these are variants of Bayesian. They are no longer variant Bayesian, but they are useful for describing human behavior. The other direction to go is to investigate more complex decision-making tasks. This is also what my lab is currently interested in. So in this morning's talk, Nathaniel showed like a video game screen. I think this is the very popular stimuli right now and possibly in the future a few years. Because such kind of tasks, in general, they can be viewed as kind of decision-making tasks, but it's more difficult and more complex and more ecological than the most commonly used laboratory tasks. One difficult computation challenge is, like, for example, this is the screen from Ponzi and Gershman's paper. And in this screen, it's a simple video game. But the problem is the participants were not informed about the rules of the game. They need to learn it based on their experience. So in this way, the possible space for the rules are very large. And for example, participants, I should say, for any, it's a space, it's not large but infinite, like it's open. So because there are so many ways you can think the game may work. So in this scenario, what you need is kind of constraint or prior belief or inductive biases. They are just different words from different areas, but point to similar ideas or concepts. For example, if you know that, this game, each game should have some way to win, then you are just leaving out many other possibilities. So you are trying to find a way to win because you know that's what should happen in a game, in a video game. Yes. Yeah, this is exactly what they did in this paper. So there is I think Carl Friston is probably the one who started this line of work, like applying the Bayesian framework and the modified Bayesian solutions to model the patient behavior. For example, many studies show that the people with autism or higher autistic traits, they would treat the information from their prior beliefs and information from the stimulus likelihood differently. Like say, it said that some evidence showing that people with autism, they will put less weight on the prior beliefs. Yeah. Um, I think in this way, the Bayesian framework is kind of descriptive. Like it's modified, it's not necessary. One thing to make clear is that the Bayesian framework itself, it does not specify like how such computations actually happens in the human mind, even in the cognitive level. It does not specify what kind of computations. It's just, oh, this is a computation. Finally we can use this to we observe, but not the algorithm. What kind of algorithm is behind this? Yeah, so in these situations, we need more complex, more structured priors to guide us through the space of hypotheses. And this kind of Bayesian inference may be combined with the reinforcement learning algorithm. Like in this morning, Nathaniel talked about model-based RL, like what this model could be, like the Bayesian, the kind of model or the world model updated according to Bayesian rules can be one kind of model that's behind human cognition. So any questions? Yes. Could you repeat your questions? Yes. Yeah. Yeah, there are many tasks that is categorization. Like each time when you learn a new concept, it's kind of categorization. And you say learn when you come to a new place, you are going to learn the social norms. Yeah, you are extracting the norms. It's kind of categorization. And also, when you're trying to infer the possible causes for some phenomenon, you are you are trying to infer the latent causes. It's also kind of categorization. Could you give a more concrete example? I'm not sure I. Yes. Hmm. You don't do categorization only when you do not need to any transfer. So whenever you need to transfer, you need categorization. Yeah, it's only like um, a teacher tells you everything what you need to do, and you don't need to like make any responses to new stimulus. Yeah. You can always develop your new models So by new models, did you mean you as experimenter or as an observer? Yeah, 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 yeah. Yeah, I think that's the most fascinating part of human cognition, and why I talk about like CRP, the model, because it's kind of model that can be expanded. And there are similar way, like if you have a hierarchical model organized in this way, then you can expand it. So it's not just like I have generated model and I just feed data to it. Instead, some generated model can be expanded. You can think about it kind of framework. Like in this case, you have some categories, but you have other categories. And in this case, we did not assume like a hierarchical kind of expandable model, but it can be expandable, like hierarchical. Yeah. And I actually have a question for this, but I leave it out for save time. Like there are many ways to test whether you are a Bayesian observer or not in some specific situations. Like a Bayesian observer will respond to if you change the prior beliefs, like if you change the statistics in the environment, and then the Bayesian observer response will be different. For example, in our signal detection case, if there are many mushrooms, and you need to judge whether a specific mushroom is poisonous or not. And if I give you 1,000 mushrooms, and all of them are poisonous, and if you are an adaptable or Bayesian observer, but of course, if you learn from the environment, the distribution, then you should learn that the best response you could give is that this mushroom is poisonous, even it looks like it's edible. What I say is, if you want to test whether observer is Bayesian or not, you can manipulate the prior beliefs, or you can manipulate a gain function. Yeah, these are ways you can test humans or animals, or whether they just respond, whether they just like choose the same choices every time, or they are adaptive to the environment. Yeah. So if it, so it's like so suppose your perception is kind of stable, but from your perception to your response, if the environment has a higher proportion of poisonous mushrooms, then your probability to say this is poisonous should be higher. And if it's lower, then it should be lower. So this is just general direction. You can also like manipulate the bonus, the gain function for this. Yeah, make some response more profitable than the others. And there are two, when we say the Bayesian observers, actually we mean, sometimes we mean it's kind of quantitatively exactly as the Bayesian prediction, but sometimes it's hard um, to know, because there's many ways the Bayesian inference can go right. Like you may not have the exact prior beliefs exactly same as the true distribution, or so the other possibility is to have more qualitative way. So sometimes when you manipulate the distributions and you or manipulate the gain functions and you observe that the observer changes its behavior, you may say, oh, it goes consistent with the Bayesian direction. And when we say observer is not Bayesian, actually, I don't think humans are exactly Bayesian. What they can do best is to approximate it. In some cases, when we say not Bayesian, we often mean that they may follow some specific algorithms instead of like to compute based on the reward, based on the prior beliefs, based on the prior distributions to choose their responses. For example, you can create two situations. They have, it's like you can apply the same algorithms, but the same algorithms can be optimal in one situation, but suboptimal in the other situation. If participants seem to use the same one algorithm in both situations, then this is not Bayesian. It's more like it's just use this algorithm. Let me give you a more concrete case. So for the visual and haptic combination case, you know, when it's Gaussian, both are Gaussian distributions, then the solution is quite simple. It's just a weighted average of the two percepts with some weight. But if the distributions or the likelihood functions are not Gaussian, if one of them, suppose, is a bimodal distribution, then the answer is not to just linear combine it, but they will have two modes. So you can, I think a strong case was provided by Coding and Warpers in their 2004 Nature paper. Like they changed the prior distributions of the, so I think it's the location of the stimulus. Like it can be Gaussian, but they also take like a bimodal distribution, and they showed that people seem to really to like use a Bayesian way to combine the prior and their percept, something like that.
One last question.
Yeah. What I should say is by Bayesian observer models, it does not specify any algorithm. So we don't know what algorithm can be behind that. My belief that it's sometimes it just we may have some algorithms approximating it. But per your question, in mating case recently is work from Griffith's lab. Like they were trying to show that the large language models, they are Bayesian observers. One interesting example they gave is like they asked the same large language model, say GPT-4, like it asked to do a arithmetic problem, like say, please multiple x by 9/5 and plus 32. And for this problem, the GPT-4 could do very well, but if you change the numbers to x times 3/2 plus 20, the answer may not be so correct. And they think because, you know, the times 9/5 plus 32 is the conversion from the Celsius to the Fahrenheit, so temperature conversion. Yeah, I think that's a very smart example. And they have future work showing that the training process of the large language models, they can learn kind of these prior beliefs and influence their responses.
You're the most Bayesian person I know, so we should thank you for giving such a wonderful lecture.
Thank you.